Okay, so now let's go to redox. That's topic 7a. All right. So we are going to start with question 1, which is on the screen right now. You should have done it, but if you have not done it, start thinking about it. I'm just going to give you 1 minute to do question 1 of topic 7a and then vote which answer do you think is correct. Okay, so let me start now. You can find the poll inside polls, meeting tools polls. Okay, so start voting. Question 1, what is the correct answer? Okay, there's 10 of you here. I should have 10 votes, I think. Okay, 5 more students to vote. Okay, 2 more students. Okay, 1 last student to vote. Okay, great. So that's the end. Okay, let me just end the poll and I'll show everyone the results. So now you can see from the polls, 8 of you chose option D, 2 of you chose option C. Now, how do you do this question? The best way to do this question is to highlight oxidation state of iron unchanged. If the oxidation state is unchanged, that means it's not a redox reaction. Okay, it's not a redox reaction. So if you recall, right at the start of redox, I have told you, broadly speaking, there are only 3 types of chemical reactions in the world. Of course, one of the types of reaction is redox. Redox reactions take up 85% to 90% of all reactions on Earth. But there are other 2 types which you also need to know, which are not redox. The first one is acid base neutralization. This is acid plus base forms salt and water. So acid base neutralization is not redox. The next one, precipitation. If you are forming a precipitate that's insoluble, all right, that's not redox. Okay, so there are 3 types of reactions in this world, and here are the 3 types. So now they want you to find out which reaction is not redox. If it's not redox, that means it must either be neutralization or precipitation. Only D fits the bill, right? This is a basic oxide, it's a base. HCl is an acid. Acid plus base, salt and water. So D is actually just neutralization. And hence the answer for question 1 is D. That's how you solve it quickly. Okay, some of you probably went to work out the oxidation states of iron in every single option. That is very time consuming. Okay, if you know that they are just asking you which reaction is not redox, then you don't go and work out oxidation state slowly already. Just think which one is neutralization or precipitation. Go for that. Because neutralization and precipitation is not redox. So this is the thinking process. I do not want to see people working on oxidation state slowly for this question because you will run out of time. Okay, so that is question number 1 of topic 7a. If you have any questions at any point, please ask in the Q&A function as well. I will get to your questions eventually. Okay, so that's question number 1. Now we shall go to question number 6 of the redox as well. So question number 6 is about disproportionation. So which equation is an example of a disproportionation reaction? So now let me launch the poll. You can find a poll for question 6. Now let's vote on question 6. Which one is disproportionation? Okay, so 4 more students to vote, please. Two more students to vote. Okay, one more student. All right, and that's the end of the poll. Let me end the poll and show everyone the results. So again, for question 6, you can see it's very split. Okay, the majority chose B. All right, but a number of you, 4 of you chose C or D. All right, the answer is B. All right, they have explained to you what's disproportionation. Disproportionation is a reaction in which the same element is both reduced and oxidized at the same time. We have gone through this in class. In fact, B is an example that we have gone through before. All right, in the redox assignment as well as the redox notes, this is a very famous disproportionation reaction. Now, how do you determine disproportionation quickly in an MCQ without even computing oxidation states? You can see that the same Cl2 appears in two separate products. One of the Cl appeared in NaCl, the other Cl appeared in NaOCl. Okay, this is a telltale sign that B could be a disproportionation because the same element is now present in two different products. Of course, to confirm there's disproportionation, you should work out the oxidation states. So, does Mr. So work out oxidation state of every single thing from A to D? No. If I do that, I won't finish the paper. Okay, I'm teaching you the shortcut to think. So disproportionation, look out for the reaction whereby the same element splits into two different products. Then you focus on that reaction only and calculate oxidation state. So I'm only going to focus on B and calculate oxidation state of chlorine in B. So over here, the oxidation state is 0 because it's an element, right? But in NaCl, the oxidation state of chlorine is -1 because Na is Na plus, Cl is Cl minus, right? So the oxidation state of chlorine in NaCl is -1. But how about in NaOCl? You got to calculate slowly. Sodium is +1, oxygen is -2. With that in mind, the chlorine in NaOCl has an oxidation state of -1. So you can see it went from 0 to +1. So the oxidation state went from 0 in Cl2 to -1 in NaCl. That's reduction. At the same time, the oxidation state of chlorine went from 0 to +1 in NaOCl. That's oxidation. So the same element, chlorine, is both reduced and oxidized in this reaction. Therefore, B is a disproportionation. Okay, so I hope you get the thinking process. Now, typically MCQs have many steps of thinking. So I'm teaching you how to think so that you don't have to go through the calculation of oxidation state one by one slowly. So I repeat, for disproportionation, you look out for the reaction where the same element has now split into two different products, like in B. Then you focus on B and just calculate that element's oxidation state. All right, any questions at this point? Okay, for the 4 of you who got it wrong, this means you must revise disproportionation under the reduction and oxidation notes. Okay, chapter 12, reduction and oxidation. Okay, now let's move on to the next poll. All right, the next MCQ we'll do, same page, but question 8. Color changes are often observed when redox reactions occur. Which color change is due to the reduction of the named reagent? This is the key, yeah? Okay, all these are color changes, but they want the color change where the named reactant, the reagent, is reduced. So let's vote now. Okay, 3 more students to vote, please. Okay, great. We are done. All right, again, I will show everyone the results. Now, the answer is D. Again, we must learn MCQ skills. Whenever you have MCQs whereby the A, B, C, D are sentences, you need to go through every single sentence, every single word in the option to ensure that it's correct. Okay? Even if one word is wrong, the whole thing is wrong. Okay? So read. So Mr. So can do this very fast. Why? Look at part A. Black solid copper 2 oxide changes to blue aqueous copper 2 sulfate. Excuse me. It's copper 2, copper 2, 2, 2. The 2 here means copper oxidation state is +2. So if copper has an oxidation state of +2 in both the reactant and product, this is not redox probably, because the oxidation state remained at +2 for copper. So A is definitely out. So the only debate here is between B and D. And this is where you need to learn. Potassium iodide, aqueous potassium iodide, is a test for oxidizing agent. How does it work? Because the potassium iodide, the iodide ions become the brown solution of iodine. All right. So if potassium iodide changes from colorless to brown, this is because the potassium iodide has been oxidized to iodine. Now this is oxidation because it literally went from I minus to iodine. This is the half equation, right? I minus became I2. I minus itself is colorless. I2 itself is brown, dark brown actually. So you can see if it changes from colorless to brown, that means the I minus in Ki has already been oxidized. So this is oxidation of I minus, not reduction. So the answer cannot be B, because B is an oxidation of I minus. And hence the answer is D. How do you know the answer is D? Because MnO4 minus is purple. Now it went all the way to Mn2 plus. Okay, I didn't balance this equation. But what you need to know is that MnO4 minus became Mn2 plus. So if we calculate the oxidation states, +7 to +2. So the oxidation state of manganese has decreased from +7 in MnO4 minus to +2 in Mn2 plus. Therefore, we say that MnO4 minus is reduced. And just nice, acidified potassium manganate 7 is a test for reducing agent. So just nice, right? It got reduced. KMNO4 is reduced by the reducing agent. Now, if you have forgotten this, you need to revise Redox Part 2, which is the tests for reducing agents and oxidizing agents. Okay, like I said, chemistry, if you read every day, you become familiar with it. This one, 10 seconds can finish. I can finish this in 10 seconds. All right, you must get to that level. Look for shortcuts, look for clues, which is what we are training now. So for the 4 of you who got this wrong, you need to revise the test for oxidizing agents, which is aqueous potassium iodide. The test for reducing agents, which is acidified potassium manganate 7. Okay, so that was question number 8 of the redox. Again, if you have questions, please ask in the Q&A. Now, if you know that for the past 3 MCQs, you have gotten it consistently wrong, that means we need to read. We have to read and revise redox. Don't just memorize. Some of you find it very a chore to read because you have no passion. You need to have passion for what you're doing. You must have interest for what you're doing. All right? So the best way is to read it every day like a storybook. Don't treat it as reading for the exam. You're not reading for my exam. You are reading for learning, to discover more. Okay, like I said, if you have not touched the redox notes since WA3, wrong way of studying. Doesn't mean that WA is over. I don't care those topics anymore. You need to catch these topics. I still read chemistry every day if I can. So should you. Okay? So that's question number 8. Next, we'll move to question 11. Okay, I believe we just said question 11 about acidified potassium manganate 7 turning from purple to colorless. So let's vote on question 11 now. Okay, 2 more students to vote. Okay, so now everyone changed their answers. So now everyone get it correct. The answer is B, okay? Again, acidified potassium manganate 7, the acidified is important, is a test for reducing agent. So if the acidified potassium manganate changes color from purple to colorless, that means X, substance X, must be a reducing agent. Okay, so that's question 11. Great. So end the poll. Not everyone got it correct. Now, the next question we'll do is from the structured already. Now, if you look at the structured section A, you will realize that question 1 looks very familiar because you have done this before in class. It's part of the Redox notes, but let's just refresh our memory. How would you answer this? First, you got to read the question. Aqueous silver nitrate reacts with aqueous potassium halide. Potassium halide. Halide is what? We have learned this word before. Halide refers to the ions formed by group 17 elements. Cl minus, Br minus, I minus. Okay? So potassium halide means potassium chloride, potassium bromide, or potassium iodide. Now these form precipitates. So now you should be able to fill in the state symbols. Right? Precipitation is always aqueous plus aqueous becomes solid. So aqueous starting materials, solid precipitate, which is insoluble in water. The other product is an aqueous salt. So that's how you fill in the state symbols for question number 1. This is testing whether you remember what's precipitation. Now, the question goes on and tells you that the precipitates are unstable and break down to form solid silver and a halogen. Okay? So these reactions are then summarized in the 2 equations. So how then do you do A part 2 to say which one is redox and which one is not? Now, I'm sure you remember precipitation is not redox. So reaction 1 is not redox. Why? It's not redox because it's a precipitation reaction. But this one, if you just write like that, no marks. Why no marks? You need to use oxidation states to explain. If you just stopped here, you're not using oxidation states. Therefore, you need to continue. So the oxidation states of all elements remains the same. Must you quote every single element out? I would suggest don't need because this is just 2 marks. All right. You may not have enough space to quote all the different oxidation states out. It suffices to just say the oxidation states of all elements in reaction 1 remains the same, remains unchanged. The one you need to calculate oxidation state for is reaction 2. So reaction 2 is a redox reaction. Why? So this is where you calculate oxidation state, one by one. So the oxidation state of silver decreases from +1 in AgX to 0 in Ag. Okay? Not just that. You should also calculate for the X. You realize the X increases in oxidation state from -1 in AgX, since it's Cl minus, Br minus, I minus. So at first it's a -1, but it became the halogen element. So elements 0 oxidation state. So this is a good way to answer it. Okay, I believe I've done this in class before. Okay, so now part B. The table shows the colors of some silver halide precipitates and the observations made when the precipitates are left to stand. Now, left to stand means what? Not that the precipitate is standing up. Left to stand means you leave it open or exposed to the air. Left to stand just means leave it on the test tube rack exposed to the air. Okay, so that's the meaning of left to stand. Now they want you to write the color of silver iodide. Now, the color of silver iodide is something you need to learn. Where do you learn the colors of these precipitates? You learned it under salts. When you learn soluble or insoluble salt, these are all insoluble salts. And I've taught you the color. The color of silver iodide is yellow. So silver chloride is white. Silver bromide is cream or off-white. Silver iodide is yellow in color. It's a yellow precipitate. All right. Now, B part 2 you can't do yet because you have not learned the trend in reactivities of halogens. Okay, we will do this probably after the EYE. Okay, of course, I will not be testing you on something that I have not taught you before. So B part 2, because it's reactivity of halogen, group 17, you have not learned the group 17 chemistry yet, so we will not do that. Okay, now up to this stage, you realize, right, the whole question got salt prep, precipitation. There's also got redox. This is a very typical O-level way of setting. They will not set one question entirely on redox only. Okay, now we're going to move to the database question for the redox, section B. Okay, now whenever you have a database question, let's revise some of the database skills. Whenever you have a database question, you need to focus on the headers, which are bolded for you. So this is about bleach and the compounds in bleach. So all of us know bleach. Okay, not the anime, but okay, bleach in this case is the detergent used to remove color or remove stains from your clothings. Let's say if a stain onto the clothes, how then do you remove these stains? All right, so bleachers can help to remove these stains, but how do you remove the stains? So the first step is to highlight the title. The second step is to read. Now, most of the words are not super duper duper important. So, which are important words? The important words are always chemical names. So, in this case, the first chemical name that you already see is sodium hypochlorite, also known as sodium chlorate 1, NaOCl. All right. Now, NaOCl, obviously, we have just done it just now in the disproportionation reaction. Okay, it's not stable. All right, NaOCl itself can react. And it so happens that it reacts with the molecules in the food stains on your clothing. That's how it gets rid of the stains, because it reacts with the stains. All right. Now, sodium chlorate 1, again, I see this word, is an oxidizing bleach. This is an important word. Oxidizing bleach. That means Another way of saying this is sodium chlorate 1 is an oxidizing agent. That's another way of saying it, right? Okay, so this is what you need to write down. Read the chemical names and write things down to relate to what you have revised before. Oh, I've learned this word oxidizing before. Mr. So taught me that oxidizing means it's an oxidizing agent. Oxidizing agents is itself reduced. Because it's an OA, NaOCl must be itself reduced. Okay? And this is how it works. So next they tell you human waste often contains ammonia. That's chemical number 2, right? Ammonia. So now ammonia reacts with sodium chlorate. And here's the equation. Okay? Importantly, they have also told you something important. It substitutes a H with chlorine. At first, ammonia is NH3, 3 hydrogen. Now only NH2 with a Cl. Do you see that? So it replaced, it substituted 1 hydrogen atom with chlorine. And in the process, it produces NaOH. So now, even without looking at the question, I know they're going to test you this. Why should it only stop at replacing 1 H? Why can't it go on? There are 3 hydrogens, right? So why can't all 3 hydrogens be substituted? The answer is it cannot. So what do you think is this blank for the next reaction? NH2Cl plus NaOCl forms. So again, the concept is what? The concept is replace hydrogen with a chlorine. Take H out, put Cl in. Take 1 H out. Then you are left with just 1 more H, right? Because it's NH2, you take 1 H out, you're left with NH. Put 1 chlorine in. So now it's Cl2. Got 2 chlorine already. Must it stop there? There's still 1 more hydrogen that can be replaced, right? So it could continue. And obviously, this is the reaction. So even without looking at the question, I know they tested this for sure. Right? Let me see. B part 1. 3 marks. Sorry, 3 marks? No, 1 mark. B part 1. You can flip to the next page. This is the answer for B part 1. The 2 equations for each of the 2 reactions which lead to the formation of nitrogen trichloride from chloramine. Okay? Now, this is what I call reading database. You read and you already start thinking what the examiner could potentially test you. Okay? And unsurprisingly, the examiner also tested you on deduce why NaOCl is an oxidizing agent. Right? Oh, yes. That's the next B part 2, 3 marks. So just by analyzing like that, I've gotten 4 marks, which is why you need to get to this level. All right? 4 marks out of 12 is non-trivial. That means you already got most of it already. Okay? Now we go on to read. So of course, chloramine reacts with sodium chlorate 1, then it reacts further to form nitrogen trichloride. We have already gotten this, okay? Now, next one is about other chlorine-based bleaches. Chlorine-based bleaches are all using hypochlorite. Hypochlorite is the ClO minus. Okay, so how then do you draw the dot and cross diagram for this ClO minus? This one is one of the questions as well, right? So first, is it covalent or is it ionic between the Cl and the O? Is this bond ionic bond or covalent bond? You got to decide. So if you recall, polyatomic ions, inside the ion, it's covalent. That means Cl shares electrons with O. Okay? So how then do you do this? If you know that it's covalent, it's a sharing of electrons. Next, you can clearly see it's a single bond. Single bond means like that. I share one, you share one. Right? It's a single bond. So I share one with you, you share one with me. The next step is to work out. Chlorine has 7 valence electrons. It has used 1 to share with oxygen. There should be 6 electrons on chlorine left, not shared. How about oxygen? Oxygen has 6 valence electrons. It has shared 1. So 6 minus 1 equals 5. The last difficulty is, oh, does that mean that oxygen doesn't look like it has a fully filled outermost shell? But let's not forget this very important piece of info, the charge. This thing has a negative charge. If it has a negative charge means it has gained an electron. So where do you think the electron gain goes to? Does it go to chlorine or does it go to oxygen? Negative means it has gained an electron from somewhere else, like a metal, right? So where did that electron go? Did it go to chlorine or did the electron go to oxygen? I think from the diagram it's quite clear cut. The electron needs to go to somewhere so that it achieves a fully filled outermost shell. Chlorine already has a fully filled outermost shell, meaning the electron has to go to oxygen. So again, we invent a symbol. A triangle in this case represents the electron gained by oxygen. Okay, and you must square bracket it, put a -1 outside. Okay, square bracket and put the charge outside. Now, these dot and cross diagrams of polyatomic ions are getting increasingly common. You need to be able to translate the structure into the dot and cross diagram. So if you don't understand how to do this, you must revise covalent bonding. And you have to text me. You have to let me know if you cannot do this. Okay? It's not optional. All right. For the past 5 years, Pure Chem TYS has been this kind of dot and cross. They do not test CO2. Simple ones we don't test really. The simple ones like CO2 is combined science. Pure is almost always like that. All right. So you need to be familiar with how to do this particular kind of dot and cross diagram, which is why I spent some time going through this. Okay. And I believe this is the answer for part C. Okay. Now at this juncture, any questions about the redox TYS? Because the rest you should do it yourself. Any questions? Now, if you're wondering how on earth am I supposed to know all this, what Mr. So has said just now is the thinking process. More important than my answer is the thinking process. Do you have the same thinking process as me? All right. How do I know this is covalent? Because the structure shows a line. A line is used to represent a covalent bond. Beyond that, one line represents a single covalent bond. That's how I knew there is dot and cross in the middle in the overlapping region. How did Mr. So know that the electron was gained by oxygen? Simply because chlorine already has a fully filled outermost shell without gaining any electron. By sharing one electron with oxygen, chlorine is already fully filled outermost shell. Meaning, if someone needed to gain an electron from a metal, it needs to go to oxygen. All right. So this is something to consider. Can? Now, before we move on, there's some space probably. I want all of you to try this. This is the peroxide ion. Can you draw me the dot and cross diagram for the outer shell? So I want everyone to work on this now. Draw on your paper or somewhere and then send it to me. What is a dot and cross for the peroxide ion? All right. I've given you the structure. Can you translate this into dot and cross? So start now. I'll give you 3 minutes to try this out. Once you're done with the dot and cross, please send it to me so that I can take a look whether it's correct. Okay, for those who have sent me, Gloria, Chen Hing, Zeli, Zhongwei, okay, all of you got it correct. Okay, so let's wait for the rest, okay, to send me. I want to check everyone's dot and cross of peroxide. Okay, Curti, you want to look at the shared electron. I think you forgot to color the circle. The dot must be colored, okay? But other than that, Curti, you got it correct as well. Okay, then Kayla, need to square bracket and put the 2 minus outside, okay? Okay, I'll give 1 more minute before I show you the answer. Okay, so it's covalent bonding for sure, right? It's covalent bonding from the way it's drawn. Okay, the single line. Okay, so if you know single line means dot and cross. Okay, this one all of you got. Now, the next step is oxygen. Oxygen has 6 valence electron, right? Group 16, 6 valence electron. If it has shared 1 with the other oxygen, there must be 5 left because 6 minus 1 equals 5. Same on the other side, there must be 5 left, not shared. And this is where I asked one of you. We know it's 2 minus. 2 minus means it gains 2 electrons. Will both electrons go to the same oxygen, or will it split? 1 electron is gained by each oxygen. Looking at the dot and cross diagram now, it should be obvious because both oxygen atoms have not yet achieved fully filled outermost shell. Both oxygen atoms are still 1 electron away from achieving a fully filled outermost shell. Hence, both oxygen atoms needs to have gained 1 electron each. And let's not forget, square bracket, 2 minus, the charge must be in the top right corner. Now this, ladies and gentlemen, is 2023 O-level. All right. So again, thinking process, the thinking process is important. I know it's a single covalent bond based on the drawing. Single covalent bond means each oxygen shares one electron with each other. So dot and cross. Oxygen is group 16. It has 6 valence electrons. You shared 1. You're left with 5 not shared. After that, you see, the oxygen has not achieved a fully filled outermost shell yet. That's why it has a 2 minus charge. It gained 2 electrons so that 1 electron goes to each oxygen atom in order to achieve a fully filled outermost shell. Okay? So you need to be able to draw the peroxide anion like this. Now, I hope you have taken this down somewhere, okay, along with your TYS so that at least you can revise from it. Okay? So now, let's go to electrolysis. So let's go to concept 4 first in preparation for tomorrow's workshop. So we did concept 4 on Wednesday before the Teacher's Day celebration. Okay. So we started off with this concept of reactivity series of metals. What does it mean for a metal to be reactive? We said in class, a reactive metal loses electrons easily. Okay? Whereas a non-reactive, a less reactive metal does not lose electrons so easily. Meaning, if I connected zinc with copper through a wire, zinc should lose electrons more easily because zinc is more reactive than copper. So where do the electrons go? Do the electrons enter the aqueous solution? The answer is no. Electrons never ever enter the aqueous solution. Right? Aqueous solution is the ionic compound, the ions, not the electron. Electrons can only travel through the sea of delocalized electrons in the metal. Metal meaning the wire. So can you see the electrons only moves in the wire? And how do the electrons move? The electrons move from the more reactive to the less reactive metal. So in this case, the electrons moved from zinc to copper. Okay? Through the wire. So the electrons never ever go into the aqueous solution. Never. Aqueous solution is the territory for ion. Wire is the territory for electron. Okay? Now, this flow of electrons from zinc to copper is useful because it gives rise to a potential difference. In a more layman terms, voltage. By connecting zinc and copper in a suitable electrolyte with a wire, you already create a potential difference, a voltage. The voltage arises because zinc is more reactive than copper. Therefore, zinc loses electrons more easily than copper will. Okay? So after that, what happens? So after you have established that zinc is more reactive than copper, what happens? That means zinc is the one that will lose electrons. So Zn loses 2 electrons. So Zn is oxidized to form Zn2 plus. Zn is oxidized, is the anode. So the zinc electrode is the anode. All right. Then what happens at the cathode? Reduction. What will gain electrons? So look at the ions present in the solution. You have Zn2 plus, you have H plus. So which one do you think will be reduced? So again, we go through our knowledge of the electrochemical series. H plus is lower than Zn2 plus in the electrochemical series. Therefore, H plus is reduced to form hydrogen gas. And that's why you can see at the cathode, which is a copper electrode, you actually form bubbles, effervescence of hydrogen gas. Now, is this electrolysis? No. It's not electrolysis because there is no battery, no external power needed for this to happen. This happens naturally. All right. Now it happens naturally because zinc is more reactive than copper. So now, how do you know which one is the anode and cathode without the battery? The answer is in an electric cell, the more reactive metal is oxidized. Therefore, the more reactive metal acts as the anode. To answer the question that just came into the Q&A. So the more reactive metal in an electric cell is oxidized. How does it oxidize? By losing electrons. And therefore, it acts as the anode in an electric cell. On the other hand, the less reactive metal remains reduced. So it acts as the cathode. So a less reactive metal like copper stays as the element. It remains reduced. It doesn't become Cu2 plus. Okay, so it's reduced. It remains reduced. That means it remains the same as before. Okay? Okay? Now, to answer the question, I believe I've just answered the question, which is the anode and cathode. But the next important question to ask ourselves is, so is the anode positive or negative? So now you need to follow Mr. Soa. The more reactive metal is oxidized because it loses electrons. Electron come out. If the electron come out, there's a lot of electron coming out. Electron is what charge? Negative. So in an electric cell, the anode is the negative electrode. Why is it negative? Because it's related to the loss of electrons. The electrons are emerging, coming out. You're swamped with electrons coming out. So the anode is the negative electrode in an electric cell. Whereas the cathode is the positive electrode because electrons are being used up. Okay? So now that we've taken this down, let's go back to the diagram. This means that zinc is the negative electrode, copper is the positive electrode. The electrons are moving in the wire from negative to positive. This is great. This is great. Electrons want to go to the positive, right? It's spontaneous, right? Electrons love positive, right? I am negative. I want to go towards positive. So that's why this reaction is natural. It's spontaneous. It's great. Do I need power? Do I need to force the electron to go from negative to positive? No need. The electrons naturally want to go to the positive. Okay? Now, contrast this with your previous examples. The previous examples for electrolysis is the reverse. The previous example for electrolysis is the reverse, right? We made the electrons travel from plus to minus, This one needs forcing. I need to force the electrons to move around in an unnatural way. That's why electrolysis needs a battery, needs an external power source. Because you are forcing electrons to move in the opposite direction that it would love to be. So concept 1, 2, 3 is electrolysis. Electrolysis needs a battery. It needs a power source so that electrons got that additional energy to move against the natural direction. Concept number 4 is a spontaneous, natural process. Spontaneous means I love doing this. No need external motivation. So what does anode and cathode really mean? Can you memorize anode and cathode just based on the charge? The answer is no. Because you need to know for electrolysis and electric cell, they are opposites of each other. So the charges, the polarities of the anode and cathode will reverse. So how then do you remember what's anode cathode? The rule that will never fail you is this rule always applies. Anodes and a red cat. So anode is the electrode where oxidation happens. Cathode is the electrode where reduction happens. So this is what anode and cathode really mean. Okay, so anode and cathode is defined in terms of oxidation and reduction. Now at this juncture, you realize, oh my goodness, so in one chapter I learned two polar opposites. I just learned electrolysis is one thing, then electric cell is another thing. Yes. Why are they different? Because electrolysis, not natural, need power. Electric cell, natural, natural, spontaneous. So it doesn't need a battery. All right. Now at the end of page 1, you can already see this is immediately going to be very confusing. Now, you are already at the age whereby things may appear to be more confusing as you go on. So how do you avoid confusion? To avoid confusion is to really read and think through, which is why I kept on stressing natural, not natural, because that's one way of thinking about it. Okay? So electric cell, which is this concept, is the opposite of electrolysis because now the electrons are moving in a direction which is natural. All right? Now, so we can make electric cells using two metals with different reactivities. So like in this case, zinc and copper. So now, checkpoint 1. Write half equations for the reactions occurring at the anode and cathode of the electric cell and indicate the direction of electron flow in each cell. Now, we're not going to do so many. We're just going to do A and B, okay? So if you don't have the worksheet with you, you can stare at the screen and write out the equations occurring at the anode and cathode. So I'll give you 5 minutes. Okay, thank you. Okay, please pardon the construction in my background. Okay, I hope you can still hear me. If you can still hear me, you can give me a thumbs up. Now, Mr. So will now write the answers for the half equations occurring at the anode and cathode. Just check your answer first, ah. Okay, for part A, these are the anode and cathode. Again, zinc is more reactive, so zinc will lose electrons to form Zn2 plus. Then you get to the cathode. Which ion is discharged? Is it zinc? Is it sodium? Or is it H plus? So between zinc, sodium, and H plus is lower in the reactivity in the electrochemical series. Therefore, H plus is selectively or preferentially discharged to form H2. So you should see at the cathode bubbles. Okay. Now next one, part B, magnesium and iron. Again, you're going to decide which one is the more reactive metal. More reactive is oxidized. So the more reactive metal is magnesium. So magnesium is oxidized. Okay, magnesium is oxidized by losing electrons to form Mg2 plus. Then at the cathode, what is reduced? So you're going to go to decide, okay, is it magnesium, Mg2 plus, or is it going to be H plus, which is the one that's discharged? So again, look at the electrochemical series. H plus is lower than Mg2 plus. Therefore, H plus is, again, preferentially discharged. So again, at the less reactive metal, you see effervescence. Okay? So the whole concept is just using two metals with different reactivities. The more reactive metal is the one that's the anode. Okay? Now, so anode is where oxidation takes place always. Whether electrolysis or electric cell doesn't matter. Okay? It will always be oxidation for anode. Now, because it's oxidation for the anode, it produces electrons. The electrons come out, flooding of electron. Electrons so minus, so minus. So anode is negatively charged. Cathode is positively charged. Again, this is the opposite of electrolysis. Electrolysis, the plus and minus are flipped the other way around. Why they flip the other way around? Because electrolysis involves electron flow that is not spontaneous, not natural, need battery. So electrolysis, the plus and minus is the other way around. Okay? But this is not electrolysis, this is electric cell. You can tell it's electric cell cause no battery. It's just a voltmeter. Now, someone just asked, an electric cell with copper and silver will not work, right? Keep that thought in mind. Keep that thought in mind. We will get to that. All right. Okay, so I'm just going to do A and B because this one I still intend to do it when school reopens. Now, moving on. So now we know how to make electric cell. Just connect two metals by a wire. The two metals must be different in reactivity. But how do I increase the voltage of the electric cell? Can I make an electric cell with much higher voltage? Yes, the answer is yes. The way to make the electric cell with much higher voltage is basically to have a larger difference in reactivity. I choose one super reactive, one super not reactive. One super high up, one super low down. Big difference in reactivity of the two metals, higher the voltage or the EMF of the cell. Okay, so this one you need to know. So in this case, which one will give you the largest voltage? The largest voltage results if you choose potassium with silver. If you choose potassium and silver as the two metal electrodes, you will realize that the voltage is the largest, the highest. Okay, so that's the concept. Larger difference in reactivity of two metals, larger voltage. Which makes sense because if larger difference in reactivity means one metal really wants to get rid of electron. The other metal really doesn't want to lose the electron. One super want to lose, one super don't want to lose. Big difference. All right? Big difference. Therefore, big voltage. Okay, now, checkpoint 2, we will do it when school reopens. Let's go on to the hydrogen fuel cell, which is tomorrow. Now, electric cells used to be made of just metals, two different metals with different reactivities. But obviously, that's not a very, very good way of doing it. Number one, metals are kind of expensive. Magnesium, for example, is quite X. You cannot make the electric cell with magnesium on an industrial scale. That's far too expensive. Besides that, if you wanted a large voltage, you must choose one super reactive metal and one super not reactive metal. The super reactive metal could be very dangerous to handle. Potassium, for example, imagine potassium handling it in your handphone. If your handphone had potassium metal, I think it's quite dangerous, right? It could explode, catch fire anytime. So electric cells with metals, while it works, is good, is not necessarily sustainable on an industrial scale. Hence, scientists have been trying their best to make electric cells without metals. Okay? And one such example is hydrogen fuel cell. Now, why do we call it fuel cell? Why don't we just call it electric cell? It's an electric cell, by the way. It is an electric cell. The difference is a fuel cell has fuel. The fuel in this case is H2. A fuel is something that you add. So, like your cars need fuel, you pump petrol, petrol is the fuel. In this case, the fuel cell uses hydrogen as the fuel. The fuel must be continuously supplied. Oh my god, continuously. Now that makes sense. It's like your car, right? After a few hundred kilometers of traveling, you need to supply petrol again. You need to refill the tank with petrol. All right. Same here. For this fuel cell, for this electric cell to work, the hydrogen fuel must be continuously replenished. You must pump in hydrogen, or else it's not going to work. Okay? So that is the only difference between a fuel cell and an electric cell. A fuel cell requires the continuous supply of a fuel. Then how come just now don't need continuous supply of fuel leh? You must be wondering. Just now, my zinc and copper, you mean don't need continuous supply ah? Yeah, don't need what? Because the zinc and copper is just a piece of metal, right? You don't have to change the zinc every minute, right? However, the zinc will run out with time as it's oxidized. So then the battery, the cell will stop to work, will stop working after some time. Okay, so these electric cells using metals, the problem is that number one, the metal could be very reactive. Number two, the cell will stop working after some time, especially if the zinc anode is oxidized completely. Okay, so fuel cell is different because fuel cell we keep on pumping in the fuel, in this case hydrogen gas. So now this is where your textbook fails to do a good job. You need to follow Mr. So now, okay? You have to follow me, okay? The table, we're going to fill it in. Are we ready to start? Okay, so first, obviously you have two electrodes, the cathode and the anode. You have an electrolyte. Now the electrolyte can either be acidic or alkaline. Typically only, we use sulfuric acid, dilute sulfuric acid if it's acidic. Alkaline, we will use dilute NaOH. Why don't we just use pure water? I think the answer is very simple. Pure water is simple molecular. So pure water doesn't have free moving ions to conduct electricity. All right. So pure water is not going to be a very good electrolyte. So we try to make it slightly acidic by adding H2SO4 or slightly alkaline by adding NaOH. Now the trick here is, depending on whether the electrolyte is acidic or alkaline, the half equations will look different. Now that's obvious. All right. That's obvious. Because in acidic medium, one of the ions you have is H plus. In alkaline medium, one of the ions you have is OH minus. Different ions, right? So the half equation should look slightly different. And this is where your textbook makes a mistake. Your textbook actually gave the wrong half equations. So now you must fill in this table properly. Okay? Now we're just going to fill in the table together. Please follow Mr. So. The first one, cathode reduction. What's reduced is oxygen gas. Okay, so that's the first half equation. In acidic medium, there is H plus. Because there is H plus, your half equation can have H plus. Again, you must memorize this half equation. How about oxidation at the anode? H2 gas is oxidized to form H plus by losing 2 electrons. So this is acidic medium. So if I were to ask you to write the overall equation, what is it? If I ask you to write the overall equation, I think very quickly, you probably will find the answer. The overall equation is just this. Hydrogen plus oxygen forms water. Oh my god. This looks somewhat familiar, but not the same as what we learned previously, right? Under electrolysis, what was our overall equation? Under electrolysis, we broke down water to form H2 and O2 gas. But what am I doing now? What Mr. So doing? Mr. So is doing the reverse. It's the reverse of electrolysis. And that's why everything is reversed in terms of the plus and the minus. The half equations are also reversed, don't you realize? So electric cell fuel cell is the reverse of electrolysis. Even the equations prove that. Okay, so that's for acidic medium. Acidic medium can have H plus, so your half equations look like this. Next, we have neutral or alkaline medium. Again, you will see a familiar friend. So watch. So if it's alkaline medium, the reduction of oxygen looks like this. Again, this is like same but different, right? Didn't we memorize this before? We memorized 4OH minus become O2 plus 2H2O plus 4E, right? Why is this the reverse? It's the reverse of electrolysis. That's why the product and reactor also switch. And finally, the last one, the oxidation at the anode under alkaline medium is this. Oh, sorry, shouldn't use red color, use black color ink. Okay, now later on you can practice writing the overall equation, but the overall equation goes back to this. You can prove to yourself. So whether it's acidic or alkaline medium doesn't make a difference. The overall equation is the same. The only difference are the half equations that occur. Now you can memorize these half equations. I think you should, because some of it is very hard to balance. But the idea is that you must get is the fuel cell or the electric cell is the opposite of electrolysis. Everything is the opposite. All right. So when learning, you already know these are polar opposites. If you are going to be confused by the opposites, you must spend more time on it, which is why I wanted to teach electrochemistry this year, so that you have more time to get past the confusion. Some of you were confused with ionic and covalent bonding, remember? You may still be confused with ionic and covalent bonding. So this is another point of confusion. Okay, electric cells are the reverse, the opposite of electrolysis in every single way. Okay, now if we have taken this down, can you give me a thumbs up? Now, what's the big deal with this thing? The big deal with this thing is, number one, the electrons go from the hydrogen end to the oxygen end. So this is an external circuit. If you connect it by a wire, this could become basically a battery for a light bulb to light up. This could power not just light bulbs, but cars. This flow of electrical current, the flow of electrons, can actually power car engines. Hydrogen powered cars run on this technology. Okay? So that's the big deal about this. The next big deal about this is, if you look at the equation, the overall equation, what is produced? It's quite obvious. The only product that's produced is water. And water is not harmful. Whereas if you had used traditional fossil fuels like petrol, petrol is a fossil fuel. If you use petrol to power a car, the petrol is burnt. The petrol burnt will give rise to carbon dioxide, which increases your greenhouse gas emissions. That's why traditional fossil fuels are not very good for the environment, because they worsen global warming due to the production of CO2. Hydrogen fuel cell will not make global warming worse in theory, because it produces water. Water is not a greenhouse gas, it's not harmful, it's not toxic, right? So that's good. Of course, it's all so rosy, man. Is it so perfect? The answer is no. Now, a hydrogen fuel cell doesn't pollute the environment. That is true in the sense that it produces only water. But the question is, may I know where does the hydrogen come from in the first place? Where will the hydrogen come from? There's no hydrogen in the air, no. Air doesn't have hydrogen, okay? So you need to know this. There are pros and cons to this thing, okay? Firstly, the good thing about this, the pros of this, only water is produced, which is not harmful to the environment. So that's the advantage of the hydrogen fuel cell. However, there are many, many downsides to it. The first downside, which we'll go through today, is the hydrogen gas. Now, hydrogen gas itself is explosive, which is why tomorrow you will see the membrane in this fuel cell is very important. You need to prevent, okay, the H2 and the O2 from coming together. They cannot meet. The H2 and the O2 gas must be at separate electrodes and stay there. Because if they were to meet, it will result in an explosion immediately. All right. Now, besides that, the hydrogen gas occupies a large volume. Gases have particles that are spread far apart from one another. This means that you will need a very, very large container or tank to store gas. Of course, do you have so much space? In a car, for example, can you really afford so much space for a gas? The answer is no. So if you wanted to make this as a car engine to power your cars, you need to compress the gas into a smaller volume, which brings back to the same question. Oh my god, compressing a gas means increasing pressure. Imagine hydrogen gas at high pressure. You just said it's explosive. Isn't that dangerous? The next problem is the hydrogen gas again. Now, hydrogen gas comes from where? Now, you have not learned this reaction, but I'll just teach you this word. Hydrogen gas comes from cracking of hydrocarbons in crude oil. So basically, we actually crack the hydrocarbons, we break up the hydrocarbons in crude oil to make hydrogen gas. Okay, you have not learned this before lah. Don't worry. But crude oil is a fossil fuel. This means that to get the hydrogen gas, I must use fossil fuel to start with, which is like, then what's the point, right? So there are many, many disadvantages to the hydrogen fuel cell. These are just some of them. So, of course, the challenge is, can we get hydrogen from other sources other than crude oil? And that's where we make all of you take chemistry. Singapore is the leader, all right, one of the leaders in green hydrogen. Not that hydrogen is green color. No, no, no. The green hydrogen means eco-friendly hydrogen. Eco-friendly hydrogen means the hydrogen comes from sources which are not fossil fuels. All right. So one day, if you learn more chemistry, you will be able to come up with sources of hydrogen which are from eco-friendly sources. Okay. And that's why chemistry often there are a lot of breakthroughs. They are very interesting. So you all must really try to learn the chemistry well. All right. So you can find a good job in such industries, right? Okay, now I know it's 10:58. Okay, we should finish. Having said that, tomorrow you will be doing this fuel cell. All right, you're gonna do this tomorrow. I'm not sure exactly what they're gonna do with you. I'm not sure yet, but we'll see tomorrow. Okay, but no matter what, you need to revise. Disclaimer. Okay, electrolysis and electric cells can be confusing. Whether you get past the confusion or not depends on what you do now. Do you read it every day? If you read it every day, it will come to you. Next, after reading, do you ask questions? Do you think, what is Mr. So talking about? Like, is it natural? Is it not natural? Why did I stress that? Okay, I stress that for a good reason. All right, now let's go on to the very last table. Give me another 5 more minutes. We're just going to do this table together. Now, we won't finish everything. Now, this table is a summary of electrolysis and electric cells. All right, electric cell is also known as a chemical cell, also known as battery. Electric cell, chemical cell, battery, they mean the same thing. Same thing, same concept. All right. Now, electric cell, there's two types. There's simple cell. Simple cell is also called galvanic cell, also called voltaic cell. These three mean the same thing. And then you have fuel cell. Okay. So now we're going to fill in the table as a compare and contrast between electrolytic cell and electric cell. So first, an electrolytic cell requires a battery. So yes, battery is needed. So electrolysis requires a battery. That's how you recognize it. Electrolysis always got battery. Of course, the battery provides energy for electrons to move from the positive to the negative terminal. This is not natural. Electrons don't want to go to the negative terminal, but you are forcing it to. Okay? Simple cell or electric cells don't need external power because it's a natural flow of electrons. Electrons are flowing naturally from the zinc to the copper, from negative to positive. Okay? Natural. So electrolysis, not natural. Electric cell, natural. Next is about exothermic, endothermic. Now we have not learned this, but tomorrow you'll see the instructor using these words. This is very simple. We have learned this in chapter 2 actually. Exo means it gives out energy. Endo means enter, energy go in, take in energy. So look, based on what we have said so far, which one needs energy to be taken in? Come read the previous row. Electrolytic cell, electrolysis requires a battery to provide energy. Provide energy, supply, take in energy. I need to take in energy. So electrolytic cell is endothermic. Electrolysis is endothermic. It takes in energy. Whereas the other two gives out energy. So it's exothermic. Okay? Now the next row, if it's endothermic, it took in energy. If it took in energy means the energy become more. The product have higher or more energy than reactants. Cause it took in energy, right? Got more energy. Product go up, higher. Alright. Whereas the other two, the products will be lower in energy than the reactants because the energy was given out. Okay, next one is the polarity, the confusing charges. So in electrolysis, the anode is positive because it attracts the anions. So in electrolysis, the anode is the positive terminal, the cathode is the negative terminal because it needs to attract cations. But for electric cell, is the reverse. This one is very important. Please learn because this might be confusing for you. All right. And finally, last two already. What is the direction of electron flow? For electrolysis, it's from positive to negative, not spontaneous. That's why it needs energy. Electrolysis is from positive to negative. So you're forcing electrons to go towards the negative terminal. They should repel each other, but yet you forced it to go that way. That's why you need energy. Whereas for the other two, it's from negative to positive. This is spontaneous. Don't need battery. Naturally will happen. And finally, we come to the energy change, which is what the physics students will be interested to know. For electrolysis, electrolysis uses electrical energy and converts it into chemical energy, chemical potential energy. All right. Whereas for electric cell is the other way around. Everything is the reverse. Can you see? From chemical energy to electrical energy. Now, so look at it. Do you see they are exact opposites of each other in every single way between the electrolytic cell and the electric cell? They are opposites. This table has helped many of my students, but you need to make sense of it. So you need to spend time to mull over it. You must mull over it. If you don't mull over it, you don't read it every day, it will never come to you. You cannot memorize. You cannot. I can tell you what happens when you memorize. When you memorize and then open the exam paper, you forgot something, your whole brain will unravel. Then you panic. So don't memorize. Aim to understand so that no matter what happens, you won't feel scared. Some of you panic because you memorize so much, but the moment you forget one small detail, your whole brain unravels. So don't do that. Okay, so I hope you'll revise this before tomorrow's session. Now, tomorrow we are meeting at 9 o'clock at Singapore Science Centre main entrance. So please be there. You need to revise this. Okay, all 4 electrolysis and electric cell worksheets from concept 1 to concept 4 must be revised. Okay, in particular, this table will be very, very useful. Of course, this table, I will also go through it when we come back from the holidays. But if you can have a head start to think through the issues, it might just help you better. Okay, and with that, I come to the end of my lesson, but stay here first because there's some Q&A, so I'll just stop the recording first.